So thank you so much again for joining us to this workshop, and it was amazing talks. I would like to thank you all. Also, it would be nice if we can set up a Slido. Maybe first of all, if there is any question from the speakers about the talks that they gave before, if there is any question, please come in and ask your question from the speakers of the morning. You have some questions on a Slido? Okay. Do you want to?
Okay. So the first question, I think, is for Jason. So what are the advantages of using KDL over using any other standard data exchange formats, example JSON, YAML, beside the predefined ontology?
So the way I'd answer that, KDL is meant to be, it's the JSON piece, but it's also coupled to a driver level component that you can integrate with your hardware. So, and again, there's not to say, like the example we saw before, bespoke integrations are definitely possible, integration with something like Green Button Go. The reason that we sort of focused on the KDL architecture is just because it has that bridging of a hardware descriptor layer as well as sort of the data layer for pickup. And it's easily, it's still human readable for a non-coder. So it can be expanded quite quickly. And especially now with integrating it with things, I think Alon's group did a phenomenal job of showing how integrating language models to something like KDL makes it possible for, again, a non-user to sort of jump in. So there's really accessibility more than anything else.
Okay, thank you. So then the next question, I think, is to Raphael. How is this different from Scylla in addition to using REST API?
Well, that's the first difference. Like, we're not using SOAP as communication. I think like the other difference is we are keeping like the integration as simple as possible, and we are keeping the templates like easy to find and easy to manipulate between people that are not like on the Scylla environment. Like we tried to use Scylla, and like our experience was like we didn't have someone that knew what they were doing, so we couldn't find like, oh, I need like this particular action, or I need this particular endpoint. So the only difference is like the simplification of like the protocol. Now that said, like we're still keeping it compatible with Scylla, so Scylla drivers can be ported back and forth like as easy as possible.
Okay, thank you. I don't know if Jan is still online, so we have a question for Jan Zhang. How did you collect the synthesis process dataset, 70K of entries for the A lab? Okay, so Jan Zhang is currently not online. We'll take this question offline. Okay, so maybe I'll open the next question to the whole panel. In your opinion, what does a closed-loop experiment mean in a self-driving and AI-driven laboratory? And a follow-up question, do open-loop experiments exist?
Who wants to start?
Go on, Jason.
Okay, cool. Closed loop to me is it has to have that element of autonomy. So there has to be at least one design, make, build cycle that's possible. Potentially, again, you can still, I think, go to not autonomous transposition between those three parts of the triangle, but you have to have sort of the basic triangle ecosystem. But passing data may be manual, passing samples may be manual, but you still have that kind of that point. At least that's the bare minimum. The best example, Acceleration Consortium. Oh, what's his name? The training lab.
Yes, Sterling.
Sterling Baird has put out a series of very, very compelling papers which define the basic minimum paper stamp necessary for what you consider an SDL, and also the sort of the frugal twin idea of, how does one start thinking of design in this space? That's what I would absolutely point to.
Thank you. So I think Professor Hein reflected on most of the points, which is closed loop is where you would connect all of these design, make, test, and analyze. But this closed loop may or may not be autonomous, as in there might be some human intervention included. It might be maybe just transferring sample from your processing unit into an analytical unit, but you are driving that through machine learning or AI-driven model, which would allow you to predict the next set of experiments to run autonomously.
I think it is open-ended. I'm a roboticist. I haven't spoken yet, so many of the people would not know the background. I believe there are different levels of autonomy or places where AI can help. It can be at the level of proposal. It can be at the level of sort of building the proposal into a process and then actually executing the process and then moving forward. When people think of closing the loop closure happens at different levels. Right? You might say the loop, I know exactly what compound I'm trying to create. I am also being told what is the exact reaction I need to do. And I'm doing loop closure locally. Locally meaning maybe the yield didn't work out. So that is automated. Of course, the characterization process or the analysis process and then closing the loop at the level of picking a different pathway. Maybe the reaction is not working out and I need to pick a different pathway. It's still the same material compound I'm interested in, but the reaction process or the synthesis mechanism is different now. Or at the same time, closing the loop at the highest level that maybe the compound or the structure of the material that I'm looking for needs to be changed. I believe you can close the loop at different levels. For it to be an SDL, at least from my perspective, the AI part is actually easy. And the easy things are the hard things, in the sense the actual process needs to be automated. Human can be in the loop at places, but like for me as an outsider, as a computer scientist or as a roboticist, I believe humans should be in the loop at the outer level. The inner loop should be automated, and that would be, according to me, a minimal version of an SDL.
So in life science, that one loop can contain many procedures. So having one loop can take weeks, months, or year. And I think that there are so many hypotheses or experiment abandoned before reaching the final procedure. And it's maybe a type of open loop result. And so I think that I'm not saying that open loop is necessary, but I think that that kind of open loop, which cannot be closed due to the failure, can be more useful if we can develop AI and robotic technology to collect the data from the experiments that failed without, and unintentionally failed. So that's my opinion.
So I think this is a great question, and we end up discussing this over and over. I think that there's a very clear definition of like what closing the loop or autonomous mean. It has more than one iteration, and there's a target that like moves itself, or there's a cost function that tries to change this experiment either on the full sense of like I'm trying a new sample or I'm optimizing a single action, and this action is optimized through every single iteration. Now, I would say like that there's also a definition for like the open loop, which would be like that's an automated experiment, and that's also pretty valid, I think.
Okay, thank you. So the next question is, what are the unmet needs in natural science labs that robotics can fill? And to fill these needs, what are the major challenges?
Yes.
And again, I think what you're going to see is each of us with a discipline chip is going to have a very different answer. For me, it still comes down to this point where there are so many problems that as a domain expert in organic chemistry, I look at the robotics side and go, well, that's definitely the hardest problem. And then we go and talk to the community and it's dead simple and it's just a matter of communication. So I still put this where our hardest challenge is actually having very different discourse and communication and understanding what the real problem is in these different points. We're still in a Rosetta Stone part where knowing how to articulate the challenge and find how that problem has been solved many, many years ago without still reiterating and reiterating. I reflect that it's now 2024, and I think I've seen these same talks and same, landmark points back in 2016, and we're still in that cycle. We're getting better, we're getting faster, but we're still repeating well, this is what needs to happen, shaking sabers. And so it's still around that communication and training, personally.
I think, to do science, you need to have good data, and data kind of feeds into the modeling software or AI that really helps you with closing the loop and getting to the optimal condition as fast as possible. And automation kind of has helped that, but then even though there is reproducibility, minimal cost, material savings, there is a need of automation to be faster. And I think that's one of the unmet needs with automation. I am an automation expert, but a lot of our users come to us asking, it's not as fast as humans, but there is a different challenge that it's supporting compared to what humans can do. And I think if automation could be as fast as humans or even faster, I think that would be a great advancement.
I'm not a chemist. I think you should. I'm just listening to the answers.
I'm researching in robotics. So I think that, I want the robot to come up with their original idea that human even cannot come up with. So I want the robot to find their own solution autonomously. I think it's necessary, and in particular for the discovery in unknown environment, or for example, if even for automation or autonomy, whatever, if the robot sees something for the first time, humans still need to teach, right? But I want the robot to come up and struggle with something new, and that level of intelligence, and also the hardware that are adaptable. Now that robot is designed so that people can easily teach, right? But if the robot has an ability to evolve or adapt by himself, then I think that the robot can can make a discovery that human would never be able to do. So I don't know, I'm answering the question, but I think it's the direction that robotic research will be interested in.
So as the non-scientist, I agree with Jason, there's still such a large gap between how scientists describe their application and what we can do as automation in the laboratory. And we spend a lot of time just asking the same question over and over, how do you do this particular action? So I think one of the needs that needs to happen before we can start doing new things is having a common descriptor that we can teach, or at least that we can train people onto how to communicate with the data people, the robotics people, the orchestration people, and the science. So.
I think I do want to add one thing. It might sound very mundane to the chemists, I believe what Kanako said is kind of true, and that can only be achieved when the mundane parts which are not automated are done completely. So you can think of ideas such as creativity or ingenuity in different levels of, we were talking about closing the loop at different levels. You can really think of injection of ingenuity at different levels. But that only really comes to fruition when you have And it doesn't matter what you call it, whether you call it automation, whether you call it robotics. That's what I would like to think generalizable, and I think in this case, specifically in this case, very high mix, low volume, in the sense that you should be able to do many things with the same hardware without needing to do retrofitting of these things, because not everybody, every scientist can effectively invest in creating a high throughput chain in their lab. In fact, it may not even be needed explicitly when you're doing very early on experimentation. So I believe creating a technology that enables this sort of very high variability, the kind of things you can do without the need for new hardware, would be the game changer.
So connected to the question was asked, what do you think of like enabling the flexibility in self-driving labs or automated labs? And also how it is connected to being fully autonomous, or maybe being as an assistive system to scientists, something that they can communicate together from human giving some comments to this autonomous lab, or also this autonomous lab provide the feedback to the human. So human sort of goes in the loop, maybe at high level at some points. If you want to show the robot how to do a low-level skill, experiment manipulation, maybe it doesn't know. So what are your comments on that side?
So I think like when we say like we're going to do a full closing the loop experiment, that involves so many levels of abstraction from like the experiment itself to the machine, that like saying like we're going to train the robot, or we're going to train our robot to do a single action of one experiment. That is such a small part of like the whole autonomous discovery, that we'll still need a human to completely describe, like I'm gonna mix some ink, I'm gonna take a picture, that's going to be a JPEG, like I need to crunch like the data like that. And then like, yes, you can train the robot, or you can train a new robot to do one action, but there is still too many layers of abstraction to be done by one single like gigantic model, or one single description of like the system.
Is there any also comment on flexibility? Also, what I meant in terms of like being assistive system and closing the feedback with the human, or also human providing the input is like at all levels, as you mentioned. Yeah.
So the problem that then is like the moment that you describe your own experiment, you already made like the whole self-driving laboratory very specific to you, right? Mm-hmm. So what would be like a different way of like doing the experiment that you already like finally described? So I don't know if that flexibility will ever exist in the sense of. Now we showed that slide of like building a facility that reconfigures itself. But this is still like multiplexing, right? That's still going to have an action that is repeated, or like one experiment that is like being repeated multiple times. Now, I don't know if like there's anyone with like the concept of doing the same experiment different ways across the board.
I personally want the robot and scientists to compensate each other. So it's different from assistive, it's different from full autonomy. It's like a searching dog. The dog has more sensitive smelling skill, but human has more ability to navigate the area, right? So with the dog and the human, we can search the area that only human cannot go, right? So I want the robot to play the role like a searching dog. So, and in that sense that even if the robot can be super expensive, if the robot can do something that the human would never be able to do, still it can pay, right? So, yeah, that's my opinion.
To add some spice to the discussion, I have questions for both of you. Mostly just like clarifications, perhaps even misunderstandings. So you said, Rafael, that there is a fixed the way I interpret at least this particular domain is, what you really want is a kitchen. There is a kitchen which has a bunch of appliances, some open-ended stuff. So not everything is cooked or in an appliance. You might need to operate stuff like you might need to make dough, and you might need to do stuff with hand. And most of the times you'll actually use an appliance, sometimes a heater, sometimes a shaker, whatever, right? And hopefully all of that is let's say, connected to the system, right? Directly or indirectly. But if you do that, if you take that analogy correctly, then you are by design fixing what you would call the API, the low-level API. A kitchen can do many things, not everything. A kitchen is general purpose, but not generic in a sense that, first of all, every kitchen may not be able to cook all types of meals. Ingredients don't exist, maybe tools don't exist. Maybe you'll figure out a mechanism. And the reason why I'm making this analogy is, in different pieces of chemistry or different types of SDL, you might need different kitchens. Right? A kitchen may also not be built for the same level of throughput. A restaurant kitchen looks very different from my kitchen. But nonetheless, the API is fixed. But fixing that API, at least from your answer, felt like you don't want to do that. You believe it should be completely open-ended, generic, universal. Why is that a wrong thing?
Oh, sorry. So to clarify, like I think the API like description should be fixed, but the lab should, like to use your analogy, the kitchen needs to tell me their resources. Yes. Like so there is like when I ask for an experiment, at least in our lab, like I go to every single instrument and I ask like what you can do. And then there's this validation step that says like what I asked can be cooked on this kitchen, or so the experiment that I asked can be done on this SDL.
Yeah, so I think that's actually very good, because then you need to know, or you should upfront, not even at every instrument level, but at a group of instrument level, the group should already have a capability list. Fair enough.
Absolutely, yes. So each of our labs like have their capability lists, and like, and especially now with this crazy LLM boom of people trying to create protocols with LLMs, we don't want like to be testing every single command. Fair. So like the kitchen can tell how to control it, right? Okay.
And again, as I said, I'm just being controversial. Kanako said that, oh, we really want to do this sort of complementary stuff, like human complements. I agree, and like that would be the obvious response. But isn't the point of SDL is to take the human out of the loop so you can sort of supercharge the number of experiments? Because if I have an SDL that is doing batch processing and data is being generated, I don't know, 500 times a day, let's assume an analysis, whatever the process of analysis is, takes me 5 minutes per sample, it's not viable. Because then a single SDL will be generating data that will require multiple humans in the loop, not one. So you'll probably be looking like, I need to, effectively, instead of creating an SDL, you created a sweatshop or an outsourcing call center where you just need to put a lot of people who are doing batch processing. So shouldn't we try to process it in a way that we minimize human in the loop? Human in the loop is necessary for certain ethical reasons, but for parts that can be automated, we should sort of automate them away.
So I don't know if I correctly understand your question, but I like to talk using the kitchen example. So there can be a robot that can imitate cooking, but I would prefer to use microwave instead of cutting the vegetable, blah, blah, blah. I would develop microwave type meals instead of repeating. So that it's a same problem solving. You know, if you're hungry, you can cook or you can microwave. I'm not saying which one is good, but it's different way of problem solving, right?
But one could argue the more appliances you use, you become rigid. Like there is only 20 types of pre-cooked meals that the grocery store sells. Yes. On the contrary, I can cook open-ended stuff, and I have full there are two use cases of NSDL. One can be open-ended, slow throughput, but really more experimental. You are really trying open-ended stuff. Yes. On the contrary, Anytime I use the microwave analogy, I could argue that then you are basically going the automation way, where we really want high throughput, less flexibility.
Yeah, so I'm not saying that the robot doing cooking is not important, or I think both of them are required, but I want the microwave meal to be something that I would never be able to cook. Totally different taste that the human would never reproduce, right? So I want a robot to come up with something totally different. So being not necessarily superior, but being different, being original, can expand the frontiers of new science.
Yeah, I think what you're describing is the AlphaGo moment, right? Where something emergent happens because of, that jumps out of the model training set, right? I think when we put, that's an easy thing to put down as a milestone because it's very tangible, right? So I totally agree there. I think that, we're kind of talking around the same, in different communities, we've heard the same thing. And really, yeah, I think the way to define it is there's really two implementations, right? There's this large, very open search going beyond what your tool would have allowed you to do before. And then the more, again, grind mundane, this is the offset, the Tony Stark suit of armor, right? Now you're superhuman because you have that capability. The analogy, and actually comes from the DARPA project we just did. The challenge they laid on us was based on the idea that if you look in like antibiotics, there are many, many molecular structures which do the same function. So there's already an innate bias that gets built in if you say, I have to make this molecule because I've decided that molecule is the best one. So the target you've thrown your SDL at is find a good way to make this one structure. But then if you look at it, it's very meta, but you're like, why am I making this? Well, because I've decided that molecule has a function of interest for some purpose. So part of the discussion around SDLs has to start with what is your intent? If it's, the example that was put to us is, imagine if a foreign power has come up with a device which will blind all of our combatants in seconds, and you have 2 days to come up with a solution. The rules of the game change compared to you have 10 years and an orphan drug that you need to kind of happen. So part of this comes down to acknowledging, kind of like what you're saying in emergent property, there's many, many solutions to a problem as articulated, and it's about building a cost function that says, well, what is the right solution based on time, energy, material, environmental impact, whatever. And it's really about changing the way we kind of do directed hypothesis-driven research to focus on outcomes rather than, single bond, single molecule, single material, right? And that's actually more challenging. When you're staring at the vast space of opportunity, you kind of freeze because it's spoilt for choice now, right? But I think that it's exactly the right time in the SDL community to start defining this, because this is where we get to say, as newcomers to the field, when you're looking at all this different opportunity, well, what are the challenges to kind of help rally behind? Are you more of a, like you say, class 1, class 2 kind of a platform? Because there's common and very different needs in both of those, absolutely.
I would like to add, like, there's a misdefinition of like what is the action, right? Like if you get an SDL that have like a DEC platform and a UR5, and now you say like, well, I'm going to open every single capability to try to be like, you're going to at some point have the UR5 like dropping, like trying to mix liquids, and you don't want that. So like defining where are the clusters of actions or the micro actions or the possibility of like each work cell like ends up like defining like what's going to be the list of possible operations or the possible protocols in different layers of this. So I agree with Jason, like there's the difference between you need to do something in 2 days and 10 years. In 10 years you can let the UR and like everything like open and like find the most magical optimal solution. And in 2 days, you probably need to use the clusters of actions and like micro movements that are already pretty well defined and known.
Yeah, I want to add that, I think we all know that flexibility brings in complexity as well, right? So if you define your self-driving lab to be as flexible as possible, when we humans operate or do science, there's a fixed set of protocol. It's like you add solid, add liquid, seal up the reactor, heat, sample, analyze, right? If you provide that STL flexibility to do whatever you want in whichever way you want, you may need, like, instead of a day, months for that STL to drive it to completion or get to the optimal parameters that you want. So you do, in my opinion, it may make sense for the STL to start at a fixed workflow that you can define, which is defined by humans, where you say, this is what I want you to do, but optimize these set of parameters. Then you can reach to your target much faster, and we are all crammed on time. I'm pretty sure you all know this, right? So you want to get to your target as soon as possible. And adding flexibility to that, I think, will just elongate your timeline.
Okay, thank you so much. There are a number of group of questions relevant to each other. I will ask them together. I will also add my questions on top of them. So one has been asking about, given the emergence of LLM and AI agent, what new aspect would expect from self-driving autonomous lab? And then it has been asking about how reinforcement learning in robotics will affect the self-driving lab. I would love to add on top of them. So I would love to know your idea and opinion about foundation model and generative AI that has been discussed a lot during the course of talks and papers during this conference. So what do you think the role of them in the self-driving lab and the works that we are doing to build them?
So to answer the first question on how the reinforcement learning on robotics, so again, you have a self-driving laboratory that is doing science that is a very high level, and you have a robot that is doing an action that is very close to the sample itself. This is just an action that is going to be better or is going to be more optimized, right? As far as self-driving laboratories go, there's so many other things happening that it's hard to tell if that is really impactful. In fact, for our assistants, because of a lot of safety requirements, if the robot's moving, all the rest of the system is doing nothing. So that will not impact us almost at all. Now, as far as LLM goes, we've been trying a lot on how to use LLMs, how to control it. And my take on that is that there's a finite set of actions or things that you can do. You can use your LLM to find the space, but at the end, the code to program the laboratory will still look the same. And especially if you have good standards like JCAN, going with the even the hardware specifications. That's just one gap, right? And you have a second one, which is the automation that will not be impacted by the LLM at all, at least in my opinion.
Yeah, go ahead.
I don't know if I understand the question correctly, but AI in general is to use the past data, right? But I think that this topic discussed here in this room is how to get the new data to train AI. So using the past AI is important, but the AI to decide how to get a new data set to train the AI is something different. And again, that it's compensated for the current emergence of emergent AI technology. So I want to keep this futuristic direction for the use of the AI in this domain.
So I have one more comment. Sorry, I have one more comment on that. Like we have one of the largest computers to train AI in the world, but I cannot imagine how big would be a foundational model to have all the self-driving laboratories premises and all the robotics premises and all the language, like all the fine knowledge that we as the implementation scientists put to put this thing to work. So I don't know how an LLM would a foundation model will ever be able to bridge all those layers. So that's an open question, I guess.
Yeah, definitely. I'd love to know the idea of Animesh about that. So your talk is about foundation models. So if you...
I believe reinforcement learning is essential or central to begin first of all. Or maybe I'm just adult chauvinist because that's my tool of choice. To answer Jason's question, right? It's like, oh, people go blind and then I really like that example. I think the DARPA example you provided. According to me, that's a level of abstraction that you need to do optimization at, right? In the sense, the search space is different, the parameter space is different. And this is what I was also saying, that it's different level of abstractions that you need. Like I was pulling up my own notes. I believe there are 5 in the sense that the highest level is exactly like I want to make compound X that is blue and smells like roses. I don't know, something like that. Right? And then the search space can be whatever, and you can propose possible ideas for this thing. Then the next level of abstraction is, okay, this is the abstraction, you might add constraints. I want to make compound X that smells blue, but in time with the list of materials and also a knowledge of yield rates and so on and so forth, right? So then that converts this into a process in the sense like, this gives you like a reaction synthesis. This is the retrosynthesis problem kind of thing. And then you go to like a KIDEAL kind of thing. Like, okay, now I'm given a process, I will convert this into a KIDEAL style structure. And so these 3 are what you would call still, according to me, they are AI assisted, but robotics free. There's nothing physical about this process. Then you go one more level to the kitchen, right? Like KIDEAL is the recipe that you send to the kitchen. And then there is plan level process, and then the low level process. And you were providing this example that we should fix the process at least and only optimize process parameters. But this is in absolute contrast to what Kanako said. The robot will never be creative. So you got to decide. If you want to do RL, you got to give it some knobs. And creativity is bounded by the knobs you give it. Right? You cannot expect the robot to find a new higher yield rate process, but only let it optimize process parameters for a fixed schedule. So it's both ways, right? And maybe the answer is, yes, we are always strapped for time, but they can be done simultaneously. There are 2 independent objectives. One is something I'm trying to do, like for example, if I'm trying to optimize for the highest level parameter, like what are the possible compounds that will do that, maybe I'll keep the low level parameters fixed. On the contrary, if I'm trying to find, if this is the parameter and this is the list of materials and I want to find the highest yield rate reaction to it, then I might want to do all of the things instead of just going with what I know. Yeah. So I believe, and that iteration, a lot of people in this space call it Bayesian optimization, but in a sense, these are special cases of effectively doing reinforcement learning.
Okay, thank you.
I don't have anything to
Okay,
add.
yeah, fine, totally fine. So I would love to go to, there are a number of questions also about simulation, digital twin. They were asking about like liquid handling, if there is something to simulate liquid, and then there were some were written about the digital twin. I want to connect with that. So there was a talk a couple of days ago during the conference, so discussing about digital twin in manufacturing, talking about like additive like value that they can have in terms of, for example, predictive failures, and then you predictive maintenance to avoid the failures in basically for manufacturing. The same may happen also for self-driving lab. So what are your comments on digital twins, their functionalities, and like connecting it also to the predictive maintenance to avoid failures? Yeah, I would love to hear.
So I'm pretty naive on robotics. Like I came like from a computer science. I still find it very hard to find a use for the digital twin. Like we have our whole lab in a digital twin, and like because every single action that we have is so well defined, like it's so like analytically like defined of like that's a pick and place or that's a liquid mixing, like and that like we are just using the simulation to like, well, will this instrument fit in our work cell? Like, can this be done? Like, can this macro movement happen? Now, as far as like predicting like failures, I think like that I'm gonna up the discussion a little bit because like there is an abstraction of failure that is not described on the simulation. If I drop a plate and it's empty, it's just annoying. Like as long as the plate doesn't drop somewhere that the robot's is gonna hit, I'll get a new plate, and that's like if I drop a plate and has nuclear material or has BSL like biosafety level 2 bacteria, that is a completely different level of failure that for the simulation will look the same, right? Drop at a plate, and how do like going on the simulation and saying like, well, that was more critical than that one. Like I don't know if there's any way of doing that yet.
So I'm more of an experimental scientist. For me, doing something in practice is different from doing something in theory, right? So digital twin could be good when it comes to predicting some of the safety concerns or some movements or testing, doing quick tests without having to run experiments. But it may not be able to predict, like Raf just mentioned, what you would actually do in practice, right? It may not be able to predict it's a BSL-2 molecule, like if you drop a plate, that's a big hazard. Like that may not come from a digital twin, and it would probably only come from an actual lab.
So in a bit of a different direction, I agree with you. I think that we tried early on to build sort of physical digital twins to the hardware as a means of a training environment, a test case. And I think we're not nearly sophisticated enough in how we choose to use them now, just again, background, to make it really, really super useful. But what has been super helpful is more digital twin of a physical system. So for example, if we're doing a scale up of a reaction, we can build a physics-based model for energy dissipation, which allows me to take a 2 milliliter 40-second reaction and scale what might happen in a 40-liter tank. So those kinds of things as a solubility dissolution, things that there's physical steps where you can build a predictive model around them, that digital twin then helps to inform what your automation sequence may look like after that.
Please.
But exactly, they don't want to have simulation. They try to, because it's too costly, so they try to do the data analytics way, and then by that try to build from the rear the digital twin. And I think that's something we could try, of course, but knowing all your mentioned is correct, sparse data, very bad quality, that's the trick. It's not easy to get a digital twin just from data and learning. And so I think from my belief at least, it will be really both. We need the experimental side, we need the human as an expert knowing about, let's say, basics. And sometimes now in a private program in Germany, we try to build both. So it's about forming technology, and our colleagues from forming technology don't know exactly how things work. So they try to do experiments, a lot of experiments, and try to build by that, let's say, the digital twin. But we see at the moment, after 1.5 years, they are still struggling with setting up the experiments. And that's, I think, for all of you who have done data analytics, it's always the same. And yeah, that's it.
Thank you. If there is any other comment on that? Yes.
Okay, thank you. So I'm also having a lot of digital twin systems because I'm in the field of life science. So we cannot kill 1,000 animals or we cannot test on 1,000 plants because it's more costly than building a simulated self, and it's not even ethically acceptable. So we need to train AI in a virtual environment. We could kill a lot of animals. And also, we can recreate the situation that can be dangerous or annoying, like for the car autonomy. To develop the car autonomy, you put a lot of heavy rain or thunder or slippery environment, right? So we can also change the lightning condition or camera direction, whatever that, using the real environment can, when the building real environment are more costly. Also, we can use virtual sensors to collect the data set that cannot be even collected using in a real environment. Using a real environment, you have to do annotation, right? And human need to do the experiment. But in a virtual environment, the things can be automatically annotated, and the information you cannot even get in a real environment can be obtained in a virtual environment. So I'm not saying that digital twin is always necessary, but in some cases digital twin is necessary, and in some cases that is not so useful. So I think in every question it's difficult to make a kind of conclusion or agreement because we are from totally different research field. So instead of trying to find a kind of conclusion or agreement, it will be important to know what the things will be in another field or another domain. Okay.
I'm loving this. I have a 4-point answer, and I think the first point is a lot of it is going back to the comment that Jason made in the beginning that the disconnect somehow is causing misuse of the tools to begin with. So let me start with first. I think, maybe I just want to be controversial. I'm happy to get coffee and drinks later. I believe digital twin is necessary. It's not optional going forward. Let me describe. If we talk of AI, and AI for robotics means it needs to move to do something, that something can be anything. And I'm sure there are things that are not physically viable, and we'll get to it. So point number one is, at the level of automation, like the physical layer of the abstraction, where the robot moves, you cannot actually build the set of what you call primitives or actions without these digital twins. How are you going to teach pouring? You might say, okay, I'm going to set the parameters of pouring here, but then, okay, I change the lab, I change the size of this thing, you go in again. Keep doing this. That is the whole point why we want to use AI. That jump of generalization does not happen without the digital twin. How do you build 20 different skills rather than one? Right? You keep limiting yourself. If you always need to change parameters every time something changes, that's a no-go. If every time you need to do an addition of a skill and it's a linear process, it's a no-go. Right? So you are really not using AI in that sense. You're basically coding things. Input is code is not always AI. That's one. So part one. Part two, I think you made this argument, and also you made this, is it will not give you safety. Of course it will not give you safety. We have physics simulators, we don't have chemistry simulators, right? So when you mix two things, the system does not tell you what happens. We only have, so you can add those frameworks, or you can add, we don't want to build low-level, quantum-level chemistry simulations. Maybe we'll add high-level abstractions, if you mix vinegar in water, this is the expected acidity. Right? You don't need it to be even correct, but the robot can learn from this information without you needing to code things up. Similarly, you said that there can be a safety incident, whether it's a BSL level 2 or nuclear thing, and a simulation will not tell you anything. I agree, it won't, but what would a real thing tell you more? I want to know this. If your real thing actually drops it, what do? You build it such that that does not happen. So all you are trying to say is, don't drop the tray. That's it. So you're not saying, if you're building it with RL, you can do what is called like risk constrained RL. You can basically say, I don't know what is in the tray. I don't care. I don't need to know. The user or my sort of designer has told me this is absolutely not droppable. This is sometimes droppable, right? And that might result in different types of solutions. Maybe if I'm handling a nuclear thing, I move slow as hell. And when I'm moving an empty beaker, it's okay, right? So that, but this is something that is not a simulation versus reality problem. It's like task specification problem. Even if you do this in the real, someone has to tell the system, this is not a go, right? So that's 2. 3, I think we need to spend time building new kinds of phenomena. The simulation that you see at this conference is basically simple physics, not even micro level physics. It may not even get FEM correct to begin with. So we as a community need to figure out what are the phenomena that we care about. And then we need to build them in. In some cases, you might just build low level phenomena, or you might have different levels of simulators. In a sense, yeah, I think you need all of these things, and there are multiple ways to use the simulator to finally do this. And I think this is the other thing that Kanako said, that simulator is the only way we can really sort of jumpstart things. Like if you ever want to do any sort of RL or trial and error, especially in an unknown setting, there is no way to discover new things completely without letting it sort of move through the process. Like AlphaGo was an example, and it was trained with a very large simulator.
Thank you so much. Yeah.
I would add, like, to tie like some of the comments, like the problem that we have with simulation is like we have so many different instruments, and some of them don't come with the CAD, like and then when they come, like they don't have the movements defined, and like and that tying that to the abstraction layer of science is so costly to do.
So just to end on that too, like, I think one of the things that we're also saying but not saying is, most of us who have been doing this are answering to funding pressure, deliverment timelines. We're doing what we can with what we have where we are, right? And something that it's sort of, okay, so I'm a physical organic chemist, which in my field, you say very quietly and you kind of, very like, because you have to wrap what you do in something so much larger because the field was seen as pedantic and real. But what that means is we're all kind of driving to these ontologies, these standards, as this kind of the real undercurrent to what we're doing. So some of this discussion is very helpful, but part of what we run into is educating the people that are making these statements around the true ROI and what that ROI actually looks like, right? To be realistic around when you will get the thing and what it takes to build that thing and what it means to have once it's done is something that, you're getting these very, very narrow conversations happening in not the broader community. So, I think that there'd be such a benefit to just laying it out in terms of it will take 37 years or man hours, whatever, right? And lay out like this is the hill to climb, but this is what we will have when we're done. And we've got, the Genome Project. We've got many, many, many reasons that show exactly what can be done with those points, but we haven't quite hit that tipping point where the justification for a huge multinational investment for fundamentals has been allowed, right? We're close, but it's still very much a, wow, this is great, but you said ChatGPT is going to make things faster, so I want this in 2 weeks. Okay.
No, I agree. I do want to add one more thing. I think one thing as an external observer, so I've been working with Alan and a bunch of people as well. Even if all of the things I said for simulation are not useful at all to you all chemists, the one thing you still need it for is benchmarking. Right now, all sort of SDL stuff is in silos. You have your own thing, you have your own thing. We don't know what you have. And then if he builds a paper, it's not like, how does that change your life, right? He might say that I have new system which has 7 robot arms and they can do 7 new things. It's like he builds a kitchen that can do new things and nobody else can benefit because replicating is not a thing. So even if for everything else, benchmarking so that the field can move forward is necessary, even if it's a benchmark that is not completely realistic. It's okay, I'm willing to take on that cost because the people need to be on the same board, at the same room, and talk the same language. Otherwise, it's just not going to work.
I really love this comment because one of the things that we tried, again, my lab, like we cannot do any chemistry, so we don't have real science to do, but it was to write the color picker, like in different instruments, and check how many man hours was necessary or how many lines of code, and compare it like as like a benchmark or at least of like human effort to build an SDL, and like that was already so hard to even like put into words and paper. Yeah.
Started with Tonio Buonasisi, right? The color match demo was the original one that Ada brought up with Alon to sort of as a line in the sand. And then we duplicated that where Sterling Systems was that version of it. It basically became the printable 3D bunny that, well, that qualifies a raw stock versus a MakerBot versus whatever, right? And because what's nice is it's an agnostic, formless task that so many people can do, but it's exactly, this is the CFAR 50, this is the CFAR 500, this is YOLO Model 1, right? These have to come into place that anybody, no matter discipline, can put them up and have the standard bench set to run your algorithm against or whatever. And yeah, it's starting to form flag for digital discoveries.
Connected to what I was just describing here about benchmarking and standardization, there are two questions, which are about our different standards for automation, OPC, UA, CILA. Is there any difference for laboratory automation? Which standard will be common for lab automation? And there is another one saying that a common theme here is everyone building their own orchestration, control scale software stack. How do you think we should address that? And I would love to add something more on top of that, which is about the role of standardization in terms of like you brought up a nice point about like the maintenance. If we want to make it open source, right, then we need a maintenance. And it's another way of like sort of going toward the standardization, right? So that people use similar tools. And again, connected to that, I would love to know also your opinion about like having like system from different companies. I know it has been like very difficult, like to integrate in a single self-driving lab pieces from many different companies. Sometimes they're not maybe compatible with each other or so on. So it takes some time to also development that. So how with this standardization, how we can try to basically overcome some of these challenges?
Maybe just one remark, I will tackle these parts in my talk.
Please.
And I will not leave it now. So just one thing, what comes to my mind, I would really love to define, especially what we discussed earlier regarding working group, what is lab automation? So I think we have a bit, it's not necessary now, but maybe at the end of the day we have some yes and no, and so it comes into my mind. I also might have a bit broader understanding. So for me also lab automation is a quality lab in a manufacturing plant assessing, yes, this quality is correct. For example, I come basically from particle board plant manufacturing, and it's very critical to assess the quality of such a particle board. And there was also a automatic lab during the time build, was much too costly, has a tremendous downtime, it never worked. So they got back from the auto lab to another one. So what is in such an automatic lab? Is it also second use case? And that's something we need to figure out at the end of the day if you want to proceed or with a doodle or whatever means, saying what is very focused and what is really out. So next question is, if you have a very, say, new technology, meaning a new forming technology, then is it in or out? So is it something which, yes, it's not a lab with a robot necessarily. It could enhance the robot, but it's not necessarily in. So if you just want to have a new technology, could be
Thank you. Thank you for your insightful point. Yep.
Anyone? So I'm going to be very cynical. I don't think that will ever be a standard. And I think like working for the US government, like we had these gigantic particle accelerators with like hundreds of thousands of like experiments and like motors. And like there were crackdowns on like, you need to use this particular piece of software. And still, like, it's been 20 years in development, and still not every beamline or everyone is using. I think the effort that we can do is like have very well defined what is going to be our premises, like, or what is going to be our primitive in our experiment. Maybe, like, for me, is the flow, or for used sample, and that will generate different orchestrators, like that, or different GUIs. Like, that's the nature of like having a student that like builds its own like experiment. But if we try to keep the parts, or at least the communication, or how we describe each thing like common, like we can reuse at least like as much as possible from each other. So that's my take on it.
So I want to start by differentiating between automation versus robot, right? For me, anything that humans don't do and anything that a machine does is a robot as well as automation, because it's something that that humans are not doing. So for example, I think of a microwave as kind of like a robot. It can do things that you're not doing, right? In terms of the standardization, what I feel is like there's lack of standardization when it comes to automation and robotics. And like we were discussing earlier, what Raf builds in his lab will not be applicable directly to what Hanada-san would build in her lab, or what we build at Unchained Labs. And this is because when it comes to integration, different vendors provide different kind of hookups for like how we can communicate with each other's equipment. Sometimes even the same vendor provides different equipment that have different means of communication. Sometimes it's just a digital I/O, sometimes it's an API driver. So just because we have one equipment from a specific vendor, that does not mean that we can communicate with all of these equipment that's coming from a single vendor. So I think there's a big push, or what I would like to see in going into the future is a big push in standardization of integration that's possible within different equipment from different vendors, as well as from lab to lab. So for example, Jason presented about KaiDL, where, you know, Lee Cronin's lab, and there's a little bit of transferability from using KaiDL from one lab to the other, right? If we could build that, then I think the research progress we can make in research is going to accelerate a lot.
Yeah, I think that I have a pragmatic one based on training my students, where every generation of student, the line we have for like standard and standard success is that the next project is better than the first, right? If we went through, and still do, many cycles where a student's thesis statement starts off very big, and very late, it's like, well, I built this new database. It's like, well, you're just replacing the one that you didn't like about the one before, and it's a new ontology, a new standard, just keeps evolving. And as the line we try to mark is exactly that whatever you've created needs to build on something of the past. No matter how you've gutted it, it has to be a step up. We have to build this kind of foundation and, you know, whatever tower in that point. So there has to be sort of marked against that progress in that point. But the FAIR standard is exactly what you use as the yardstick, right? It has to be transferable, utilized by somebody else that wasn't you. And we're aspiring to be, you know, the 3D print or the PDF kind of a part, right?
I think this was another discussion that came up, is we cannot define robotics. Robotics is open-ended, and then you solve the problem, and that problem becomes automation, right? Grasping was open-ended 8 years ago, now it's automation. It works in the factory, you build a system around it. Automation requires a lot of frameworks, tooling, design to make the system work day in and day out. So I think there is that. In this particular SDL case, I believe we should not lock ourselves in for two simple reasons. One, it's not clear that the hardware that we have currently is sufficient or ideal. Hence, there is value in what I would call doing robotics here, because we have not yet converged to what the optimal kitchen is, in a sense. So that's that. Then at the same time, we need to do standardization either through data sets, through these like hard sort of realistic physical but standard objects, and then also simulation and digital twins. I believe, and this is me speaking with my industry hat on, if a company comes up with an API or a standardization, it will not be accepted, because there are for-profit competition that has no incentive to accept that. So it does need to come up through some sort of consortium or open source benchmark, like the users come up with the standardization that the manufacturers need to follow. So this takes energy, but it's definitely doable. It has been done in so many other fields that it is hard for me to understand that it won't work here.
Yeah, I guess a less bleak comment from my first one is your kitchen analogy is pretty good. We're pretty good at following recipes and going to a new kitchen and doing it, right? So at some point, like we'll need to bridge that. Like, I think that's where robotics will come in. Like,
So yeah, we are about like 5 minutes to finish the panel discussion. I have so many other questions. I have like two, I would say, major question. One is about the role of sustainability and safety. We didn't talk much about sustainability and also ethics in our development in the morning. Hopefully we will have it more in the afternoon. And then also I have another question about community building in terms of like connecting the robotic community with the basically people from scientific background. I think it needs a major effort on that side. So you can take whatever of these questions, and yeah, I would love to know your opinion on that.
Maybe I'll comment on the safety side. So during my presentation, I talked a lot about why, chemists or researchers would want to use automation. And one of the reasons is for safety, right? When we're doing research, whether you're working with chemicals or biomolecules, safety is one of the biggest concerns. And humans being impacted by chemistry or fire or hazards is not replaceable, but you can replace robots. We have a lot of customers using our robots for basically radioactive materials, right? And having humans interact with those kinds of materials on a day-to-day basis can cause a lot of safety concern for the human health. And robots can be a replacement for humans. The other part of the safety is using the robots and having them in a safe environment. So these can be handled by what we would call enclosures, just like ventilated hoods or BSL safety cabinets, where robots are enclosed inside these enclosures, so that humans, when interacting with these robots, they still have the safe environment around them.
Thank you.
so I guess specifics apart, like science is pretty unpredictable and we deal with very dangerous things. So every minute that you save a human from being inside a laboratory that have like something that is incredibly dangerous is worth like all the effort that we are putting here.
Thank you. And about the robot community building, like, is there any comment?
That nobody can be expert in material science, life science, robotics, AI, and automation, right? So even, we believe that we are discussing the same things using the same specific terms. Maybe we are imagining totally different things, right? So that the proposal of consortium is very, very important, and also to find a kind of primitives that they mentioned that, that there is a robotics challenge. They have one task And by achieving that task, it means that the robot is somehow versatile, right? So of course I mean, it's not the design of the kitchen, but it's a design of the dishes to make. Like, for example, if you can make a curry rice, you would somehow expect that this person can also cook stew or other standard meals, right? So that kind of standardized primitive tasks that can cover challenges in material science and life science and AI and robotics and automation will be very important. And you cannot come up with an answer by yourself. You need people from different diverse research fields. So I think we need to have a kind of consortium, society, or whatever to have a network of the researchers who are interested in this field.
Yeah, definitely. Yeah, with that, I would love to know maybe if you have any final remarks you want to bring it up. If not, okay. So thank you all so much for joining us for this panel discussion. And let's have the round of applause for our panelists, and then we can go for lunch.
To add that it takes a lot of energy, and the purpose of workshops at these places is indeed to bring cross-disciplinary people here. As you said, building the community would be the wonderful thing. So a round of applause to all of the organizers. It took a lot of effort, multiple months of planning to get here. So thank you all for bringing us here.
I would like to also thank again from all the co-organizers, that some of them are not also here today, unfortunately. But yeah, thank you. So let's be here around 2 p.m. We will start with session 3 of the workshop. Thank you. Enjoy your lunch.